Today, I'd like to talk about continuous profiling and how this can help you in a SRE day-to-day life, solving your incidents, get some more ideas where to look deeper, ideally finding the root cause. And yeah, so my name is Christian Simon. I'm based in London and I work for Grafana Labs as a software engineer. So we don't really have embedded SREs, so every software engineer is also an SRE. So we run our software ourselves and obviously encounter all of the slight problems of our future work ourselves. So before I was working on our continuous profiling product, which is called Pyroscope. I was working with Loki, Mimir, so all of them are open source and kind of available on GitHub. Like, definitely chat to me, reach out if you have any questions. And like my way diving into observability was through Kubernetes. Like, I probably come from the Linux sysadmin side and then got more and more into software engineering through the arrival of Kubernetes. So I want to maybe quickly look at different signals we have in observability. I think we're all familiar with logs. Nearly every application should have logs, somewhat at least. And they help you to pinpoint something to a singular problem, like get a descriptive error message ideally. I guess their challenges are there could be a lot of volume. You might not be able to afford to log everything. And the formats are really not standardized. So obviously we might have now a JSON log format in a lot of applications, but it's still hard to get kind of information out in the same way. And like the signal to noise ratio might be quite bad in the sense that it's really hard to see the things you want to see. Like, you might have errors in too many log messages to just filter for error in there. And it's hard to spot them. Then we have metrics. Metrics tries to tackle a couple of those log challenges. Look at aggregations, look at how your service is behaving across all requests, and maybe figure out where it's not behaving to then investigate a bit more. Obviously, like with all kind of aggregations, you lose some kind of resolution, but it provides you an accurate overall picture. So quite typical are the raids, error raids, and the latency of your service, to like the red method as we call it. And obviously, like, because we're only storing an integer, it's relatively small compared to log message strings and so on, and fairly cheap to aggregate them further, query them over long periods of time. Then we also have traces. So traces are really helpful for this kind of microservice world like that a lot of us live now. So we get to see kind of how a request travels through your system. Like, you will be able to see the particular pods involved. You can attach more information, like also log lines can be there. Also, like, your metric system might be able to kind of give you some example traces. So, like, for example, in, like, I don't know, like with request durations of 5 seconds, look at this trace that took 5.5 seconds. And so you can figure out what maybe has gone wrong that this request took so long. So with traces, there's a lot of data to be collected, and often you would sample what you want to have traces for. And so, like, maybe the thing you're looking for is not sampled, depending how well your sampling mechanism works. And so now I want to add a fourth thing to that, and that's profiling. Obviously, I work on a continuous profiling database, no surprise there. But basically, like, where profiling kind of steps in, you might have identified a problem either in a trace, through your metrics, and then you want to understand more about it. And obviously, someone might have put down some helpful log messages in the lines of code you care about. But with profiling, you get a more generic way of figuring out which line of code might have produced that problem, like introduced some kind of performance problem. And like you can basically like used that. You were able to use that probably for longer than I live. So like I think profiling was always a thing. But what is now the possibility to do it continuously across your whole fleet, maybe even, was the introduction of some more sampling there. So obviously, if you want to collect every code path, every increment of an integer, like obviously those operations are super efficient, small and quick. And if you want to record them, it costs you a lot more in overhead than like the actual business logic. And so that's like the sampling kind of steps in and makes sure it only like collects things that are significant enough to make a difference. And so like often you would come maybe at a problem because a trace shows some form of overload. Then you go into metrics, you maybe find the pods that have too much CPU usage. And then through continuous profiling, you could look more into detail and scan why and where the CPU is spent in that particular pod. So in general, like there are a couple of use cases why you would want to do that. Obviously, like reducing your cloud spend, you want to be as resource efficient as possible. And like maybe you do unnecessary work, and like sometimes it's not obvious. Maybe your predecessor in your team has written the piece of code and you haven't fully understood the impact of it, or you wrote it yourself and haven't fully understood the impact of it. So with that, you can have some kind of real data, how much CPU time is spent, and like you can break it down to every line and see if it matches with your expectations. So for example, if you compress something, it's known to be CPU heavy. So like, I guess no surprises if you see a lot of gzips and a lot of functions like that there. The other use case is to lower the latency. Obviously, like you want to service your SREday users, as we saw in the talk before, or maybe like general your online shop. Like if a checkout takes too long, maybe you're not converting, and like by using first a trace maybe to pinpoint a pod that might be slow, you can then dive in a bit more and maybe realize there's some kind of I/O problem or whatever it might be. And then I guess the final great use case is to reduce your recovery time in an incident scenario. So you might start with like, oh, this is ooming, this uses too much CPU, and then maybe your initial response is scale up, more nodes, more pods, more everything. But then like obviously like you don't want to pay that bill long term. You want to understand what's going wrong and want to look into. And I think that's what I'm going to focus for obvious reasons today. And so how would you usually like interact with a continuous profiling query? So like obviously it starts all with defining what kind of pods, what kind of namespaces you want to query, and what profile you're going to look at. So bit after that slide, I'm going to look into the different types of profiles that are there, and what they can reveal. So then also within the query, like you can have like the standard kind of, I don't know, define the time span you want to look at, and then once you send the query off, you will get back the resource usage over time. So this is the only thing where you can kind of see the over time kind of aspect of it, because the flame graph and table, and that's quite important to understand, will give you the aggregate over all of that time period. And you might see some spots where it's peaking, but like it's not super clear what is going on without like zooming further in the timeline. And then you see that in the flame graph. So to understand a bit better like how a flame graph should be read and what you can actually, or what you should look out for, I have a bit of a pseudocode example here. So there's like a simple main function that does a bit of work. First a lot, then a little, and like those functions kind of call each other. And maybe we look at the CPU aspect of it. So like the main method itself spends 3 CPU cycles before it then goes into do a lot, which then calls prepare, spends 5, and then do a lot spends 20 CPU cycles. And so the way the kind of profile gets recorded would be a bit like this. So you get your your kind of call stack, and at every point in the call stack, you would record, I've spent 20, spent 5 CPU cycles, and so on. And obviously, like, this happens with some sampling, as I said. Like, so maybe those 20 are even not enough to be sampled here, but like, let's just assume for the purpose of that demo, it is. And then when you want to visualize it, you quite typically use a flame graph. So you can see again, like, how from main you go either into do a lot or into do little, and both of them call prepare. A flame graph's colors, there's not really a clear standard. Like in our kind of product, you can even select what you want to color. So I think we color by default which package it's in and the function name. So some just do it randomly to look like a flame. There are various ways you could do this. I think that the more important thing is like to look for the edges of the boxes underneath where there's nothing, because that means time has been spent. So I guess in our sense, we kind of come into total, start with main, and then we can see like there's a really small bit missing. So main spends a bit of CPU. But then within do a lot, you can see a huge gap in the kind of succeeding called function, which means do a lot, spend quite a lot of CPU, and I guess in the same way, do little spends only a bit more than main. So what you're looking for is kind of look a bit bottom up and find those edges and see if do a lot should really do a lot. And if it shouldn't, then maybe this is a good candidate for investigating why it's actually doing a lot more than you expect it to be.
Wait, isn't that an icicle graph?
It's an icicle graph, yeah. Like, I don't know, like I just accept that the world is turned around. We are maybe in Australia. No, I don't know. But yeah, that would be also a good name. So you can actually like later play around with that particular example. Quite often you would also see it in a table. I'm not too sure. I think I removed that slide. Yeah. So now I want to look at the different profile types that we can collect. So at Grafana Labs, we do a lot of Go things, so it's a bit more Go specific. But for many languages, you have similar kind of concepts, similar profilers. A CPU profile is basically measuring the time when your code runs on CPU. And for Go, that means when your Go routine is executing. So there are like 3 states: runnable, waiting, and executing. So you would be waiting if you wait for a network response, not visible in a CPU profile. And also when you're not getting scheduled because of some congestion of other Go routines competing for scheduling on the CPU, also not be visible. So in general, like, you wouldn't find kind of locks, I/O, syscalls are often not very well visible on CPU profiles. So you really only see the pure CPU time. And often when you first collect a profile, maybe see how the total value of your profile is. Because if you're trying to optimize something that is very low, like you will find there's not much to optimize because you're not running on CPU much, and maybe it's not the best use of your time. Something to help make those visible is like a separate kind of instrumentation library. It's called fgprof. And what that does, it actually measures the wall clock time of every Go routine. And it makes visible those I/O waits, like waiting for network, time sleeps. And yeah, like, there are definitely some problems when I think you have a lot of Go routines. The overhead might grow quite large. But in the demo later, we will see a bit how that actually helps for at least the lower to middle scale programs. So we only collect those, I would say, for our operational clusters on demand, kind of adding an annotation, like if we really want to see this. And like, that is kind of part of a separate library. Like, while Go has, for example, a CPU profile in the standard library, and it also has the memory heap profile. So Go as a garbage collector language, obviously, like the more you allocate, the more garbage you create, the more CPU time you will spend like identifying it and clearing it up. And so often you will find a very busy application. This CPU profile will show somewhere between 5 and 30% of garbage collection time. And then once you see such high percentages, I think it's always a good start to look at allocations and like see where you may be allocating too much, like you should reuse already allocated memory that is otherwise not referenced anymore. And basically the two subtypes of the memory profiles are the in use, which is what is currently still held, and the allocs are kind of what has historically been allocated and been thrown away already. So we also like are subject to some sampling. So like roughly, I think every 512 kilobytes would trigger a stack trace being added to the profile. But they are then kind of multiplied roughly to see the actual values. Like, don't be surprised when your metrics don't match what the total of the profile is. There's a lot more going on that is not covered. For example, like stack allocations wouldn't be covered. Like you will only really see the heap. And so that, yeah, it's as usually sampling introduces some kind of inaccuracies, but also an important fact is often the problem is that something is not getting freed because you're still keeping a reference to it. And the profile won't tell you where that reference is. You need to figure that out by using the source code yourself. Because often like the problem is not where you allocate it, the problem is where you kind of keep the reference to it with some later code. So now I want to look at a couple of incidents that we had. So we started the project maybe June 2022 with 2 people and like are now like maybe a team of 7 engineers, I think. And like about 6 months ago, we kind of rolled it out to teams that were interested. Now everyone gets it, even if they're not interested. But for example, as part of a different incident that caused some downtime for a particular dedicated cell, so for one customer, we were able to kind of find out, and we're going to zoom into the flame graph a bit more, so you don't need to try to read it, but like we were able to find out what actually like we were noticing for years. And so if you look into that kind of flame graph here, so what we're looking here is Go routines. So that's a bit like threads in Go, like tinier threads. And we have the count of how many Go routines are spun up. And so like obviously the K here maybe might suggest we're looking at memory, but like it's actually 800,000 Go routines being kind of active somewhat. I think a Go routine is maybe around 8 kilobytes already. So that's already a couple of gigabytes of memory allocated. But basically what is going on here, we have a circuit breaker that should, in theory, protect the system from allocating too much memory. When something happens downstream where we can't write to disk, write to the bucket, whatever. But basically the problem here is, like, you can see a lot of logs in those call stacks here. And the problem is, like, we have that Go routine running that tries to log the error that the circuit breaker has canceled the request. But because there's so many logs going out, we can't write to the log because we're waiting for the log to write the so that you can see like log slow, new ticks acquire. And basically like we realized that in a situation where we're losing or have to throw away data to protect the system, it is not a good idea to log every line and even cause more disruption by that. And so in this particular case, it didn't help to solve the actual incident where we reduced or moved, I think, across different regions, or I can't remember exactly. But basically, like, we created a bit of an overload that then triggered this. And then because we had continuous profiling, like the profiles were looked a lot by a lot of engineers, and we spotted that problem and made the fix, I guess, a couple of days later. And so now we just don't log those anymore. And I think since then there's also been like some more kind of rate limiting on logs, and that hasn't become a big cause for making an incident even worse. So in another case, like the low-key team which I was working on for a long time, like in this case, we actually helped to identify what was going wrong. So we have like SLO multi-window alerts, and we basically were breaching. It got alerted. And usually our databases have like a fairly separated write and read path to make sure we don't lose data if someone queries too much. But the problem is the recently received data, which is queried the most, is kind of also required for the read path. And we call the component the ingester, and the ingester basically holds both. So like, it's important for the write path, important for the read path. And for a while, there was a lot of suspicion around object store rate limits that we have been hit in the same cluster for a while. And so like, it took a while for us to realize that the problem is not actually the write load. It was some read queries that made the write path slower, because kind of this shared component between the two. So I guess it only really dawned on us when we looked at that CPU usage graph, and I guess you can see our like the darker blue is the query here, and that's obviously query read path only component, and we were basically investigating a lot of ingesters, and only when we saw that dashboard we finally like managed to pull a profile and like for example, again, like the biggest one without anything beneath is this kind of tree, and you can see it goes into regex evaluation, and someone has sent us fairly large regexes, like a lot of string or comparisons, I think, and that basically like caused a lot of CPU usage in the ingesters and helped us, I guess, to understand the problem. Like, obviously, usually, like, scaling up is the first thing we would do. I think it didn't have that much of an effect, because scaling up ingesters will rebalance the system, add more load to an already quite overloaded system. So the solution here was to limit the particular regex tenant down, like, to less query parallelity, and then we were able to handle it. And then, like, in the meantime, we introduced some limits that would limit the length of bytes of regexes. And I think longer term, like, we always had the plan to separate that ingester component into the read and the write path a bit better. So we wouldn't lose data, especially when like there's some large loads of queries going on. And that has now become a lot of traction since that particular incident. Yeah, so like I'm basically like now at the demo part. So I created just a quick client-server application just to show maybe how you would look into things. Like it should be like a fairly Helm install kind of setup. So I hope the demo gods are kind of helping me today. So basically, like, yeah, I'm deploying 3 pods servers, 3 pods clients. They talk to each other, and there's a bit of time sleeps going on and slow network requests. And we wonder how that, yeah, kind of will manifest. Yeah. Should have kept it running. I should have it locally. so yeah, that basically starts kind of the single component Pyroscope, and also an agent that will do the collection, send it into the database. And now I'm starting the kind of client-server application. So we should see a couple of pods running fairly soon, hopefully. Yeah. And now basically like I just pull forward into that Pyroscope component. Sorry. And so yeah, by default it will just show you a profile it thinks you might be interested in. But generally, like you would get a selection of kind of different workloads that are running, and now also the client and server show up. And so like when you look into the kind of particular workload, you will also see what is collected. So yeah, we have the go routine, memory, process, CPU, and so on here. And then actually the one that I wanted is not here. But let's look into the CPU time. And I'm gonna show quickly the source code. Is that somewhat visible? Hopefully. So yeah, it's basically like a sleep endpoint in a HTTP server here that gets called from the client, and so you kind of can simulate network calls. There's also like some heavy CPU computation going on, and like I basically just want to show how they show up differently here. So this is the CPU profile where we don't see those sleeps happening, and so you can see that the CPU intensive task is like dominating the flame graph here. So yeah, it's like 83% of the CPU time that is measured, while everything else is fairly small. And that's just for the reasons that I said before. You don't capture the network weight in that profile, so that's why the other ones don't show up. And what I double check. I can't get the feature FG code to I, but to show the same thing. And so like what is really useful then is the kind of diff view. So there you compare kind of the relative distribution of your flame graph with a different pod or a different time. So in this case, we look at all the 3 pods. I guess, yeah, it usually like is helpful to look at different pods. If you isolated one pod that is misbehaving, or if you know like maybe 5 minutes ago everything was fine. I want to understand what the difference now is since then. It can be quite. And so basically like on the left side I have 2 different timelines. So like for example here I select the beginning versus the end, or like so like the startup phase here of the client versus the like when the system is running. And we can see the green bits here, they are things that are no longer happening, while the red bits are new. So more CPU usage on the red bits in the right side, and the left side, the green, is kind of what is missing now. And so I can now kind of maybe zoom in here. to see a clearer picture. And in this case, we actually see our profile collection. So, basically, like the pprof itself, like takes some overhead of your system, and like you can see kind of how that has changed. So like in the red case, we have a Go routine profile, and in the green one, we collected a heap profile. And obviously, they have slightly different call stacks from the write to method onwards, and so that's kind of the difference. And let's see if I can find what I actually wanted to show. And so like the thing I actually wanted to show is here. We can see that red, so we added CPU on the right side, and that's here the persistent connection kicking in. So when you open HTTP 1.1, I guess keeps the connection open if you don't send the header. And like, for example, this is like maybe some maintenance read loop from Go, keeping the connection open or checking that it's still alive for the next of those client server requests. While maybe the green one is opening it, and like often that gives you quite good clues what has changed, like maybe what's going on, what part of your system gets queried. Like kind of that's how it showed us the regex. Okay, so that was it pretty much from my end. Any questions? If I still have time.
Yeah, why is removals in green and red is the additions? It's like the inverse of a diff.
Yeah, like it's a bit annoying in the sense like you won by using less CPU. That's why it's green. I think you could change it somewhere. Like I recently, I think if it bothers you, you can change it to blue and red. Don't know if that's better.
Yeah, that's more more neutral.
Yeah.
Okay, so this is all like very Go specific, right? It's just using people like are there any plans to extend it to like the rest of the world?
The rest of the world. So there's multiple efforts going on. I guess a lot of people maybe are aware of eBPF.
Yeah.
So the agent that I use can be configured to collect eBPF as well. Generally, eBPF is not collecting memory right now only for a few languages, maybe. I think there's nothing really speaking against adding that, but like it is a lot of work understanding the runtime from the outside. Like the next release of Grafana agent will also use like other profilers, like for example a Java profiler that will kind of just be attached to a Java process. And I think with eBPF we support Python for CPU profiles, like Rust, C. Like generally, like compiled languages are a lot easier to understand if you compile them in the right way with debug head. So like there's a lot of ifs.
Yeah.
And I guess with Go you need to export that preprof endpoint.
Yeah.
And
but this is literally coming out of the box like this, right? Once you run the profile,
yeah,
right?
Okay. So like you can maybe compile it in a way to remove those symbolizations, but like the standard Go binary will kind of just come out there. Sweet. And like the good thing is like you don't need to kind of remember adding a metric or remember adding a trace somewhere where you care about. Like you will just have everything.
Yeah.
And in theory, the data is also there to actually get the line of code, which is not in our UI. And obviously we don't have the source code in the backend right now, but like this is definitely something where we want to go going forward.
It's pretty sweet. I mean, it would be lovely to get like a C++ app to have this kind of
so like I think C++, if you compile it with the debug headers, you should get similar things. You can also download the profile and analyze it further, like with pprof.
All right, any questions, guys?
All right, cheers for the talk. I was just wondering how the diff works. So like, for example, if you would select 2 time windows where there's not much in common, like does it figure out what's in common and what's added and removed, like in a file or like?
Yes, like if there would be really nothing in common, and maybe I can kind of show you that. It's not that easy. So let me just try. So like, for example, I'm comparing server, client and client.
Yeah.
But now maybe if I compare server and client, we might find there's not really much in common. So there's a lot of red and a lot of blue, and this might be some Go stuff that just is the same because it's part of the runtime. And then in the same way, when you maybe reset it, let me quickly get it back. Yeah, there's a couple of bugs in our front end. So, but when I kind of select roughly the same time, or like after it's running, you can see those getting quite small. The diffs, yeah. Still a bit too much for my. Like obviously they do different things. I guess if you really select over 5 minutes, where they do like repeat the same task over and over again, you see like there's really nothing different. Like a bit of red, like I don't know, it's
percentage-wise,
yeah, 0.58%. So like that's obviously statistics and sampling.
And if you select on one side just a very short time window, very large on the other side.
Yeah, I guess that shows you then what the difference of that very moment is. So like I guess in that very moment, like this was not happening. If we look into, might be the profile, for example, gets I think I have 15 seconds as a setting. And so yeah, your resolution on those top should be 15 seconds. But obviously then it also, you don't see it if it doesn't get collected, I guess.
Yeah, makes sense.
Yeah.
And you have the same for memory as well?
And for memory, I guess what we do here is not really too memory intensive, so I don't expect any. So like, let's look at the in-use, which is kind of, yeah, so you can kind of see profile collection is fairly memory heavy compared to everything else. So you can see, like for example, the compress here taking up quite a bit. But yeah,
that's not up to scale, right? It's just still different. These are the values for this particular function.
What do you mean with up to scale? So like,
I mean, the more memory wouldn't have like bigger.
No, like so, like you always need to look at the bottom.
Yeah.
So like, this is 30 megabytes, and I guess if I click into the compress, it will be something like 8 or something. 9 megabytes.
Yeah.
But like the diff comparison will not look at absolute values, because the idea being when you like want to only look at pod A and like pod ABC, then obviously the absolute values will be different. It will only look at the kind of relative size of the boxes to each other for this mode.
Great. One more question.
Thank you. So yeah, I never did like continuous profiling. Usually just do profiling when there's like a perf test that shows that it goes slower than usual. And I was wondering what is exactly the overhead you have by experience.
Mm-hmm.
And also I'm kind of used to see these flame graphs on like a static period of time. It's kind of hard to me to imagine like on the continuous, you know, if I have a metric like, I don't know, request time, I can see the graph and I can see like how it goes up and down and relate to events, and this is kind of hard to see, right?
Yeah, I guess like for the time view, like I guess you can see like we look at very short times and like there's not too much variance. Like maybe I can, it's been a while ago since I started, maybe I go to 15 now. So maybe you get a bit of a better idea, but like what do you need to do? Like the selection is crucial to get the flame graph where you care about. And then like with the diff, you can also like, I don't know, like why is it so quiet in one of those lower CPU times? And then you can kind of see maybe, yeah, because it never got a profile request and never did anything. So like, I think the diff view is quite important for that time component, because like, otherwise it's just an aggregation. Like it will like be lost in it, or you need to remember this block has been this size and so like I guess so we're looking now at, and I'm getting confused with those colors as well all the time, at the green bits, and obviously like maybe like it looks like this no profile has been collected. That's why the CPU is so low in those two collected profiles versus the other ones compared to the average profile. So, like, what was the first part of your question?
The first part was, what is the overhead of
The overhead.
running it in production?
Yeah, so like, I think this is really difficult to answer. If your application does nothing, the overhead is infinity, or 100%, I don't know. But so we see, like, in our kind of cloud, we see an overhead of like somewhere 2 to 5%, but like we have very busy things. Like they do data, they receive data, write the bucket. Like there's a lot of things going on. That's why it's so small. Like if it's a web service getting sporadic traffic, I guess it can be 20%, I guess. So we definitely want to, there's the hotel demo. So we want to kind of start adding that and measuring 2 environments to get better numbers while we do a load test, because it really depends on the load. But obviously we want to have some checks on it that we not doing anything to make that significantly worse, ideally better. But I think you need to figure that out a bit yourself. Like often you get a lot of value only scraping 3 out of your 300 pods, and only when you have an incident like maybe cast the net wider, and then obviously then you don't care maybe so much about overhead. But it could also be the thing tipping you over the as you see there's a bit of memory involved, and so yeah.
Thank you.